Okay, we've seen that the function, vector function, big R of little r theta, defined by this function, has r derivative and theta derivative as indicated. We've shown in some detail how the surface area of this hemisphere should end up being equal to the integral of this cross product of these two vectors. Magnitude of that cross product integrated with respect to r and theta. So we proceed to calculate first the cross product. Now, cross product, we can use the determinant definition. When there's a missing variable, I'll generally simply use the distributive law, so that I'm going to be multiplying each component of this by each component of this. The I components, the cross product of I with I is 0. Cross product I cross j is k, so that the I component times the j component here is going to give us r cosine squared theta times the k vector. Now the cross product of j with I, j cross I is negative k. So that these two components are going to give us the negative, but this already has a negative, so that's going to be plus r sine squared theta. Now that's kind of nice, because that's also times k, so that we're going to have a cosine squared plus sine squared. We're just going to end up with rk. Then rk by each of these vectors, okay? K cross I, and you know, always good to have the right hand rule. K cross I is j, so that we have minus r squared sine theta over the square root of a squared minus r squared. And then k cross j is negative I. So let's see if we can get that on here. We're going to have a, okay, let's see, that's times I. And then we're going to have a plus r squared cosine theta over the square root of a squared minus r squared times j. Now it really doesn't hurt a thing to verify our work by doing the cross product, the determinant form. So that's going to be the determinant of the matrix I, j, k, cosine theta, sine theta, r over the square root of a squared minus r squared, and then negative r sine theta, r cosine theta, 0. That's going to be I times the, we'll go ahead and expand this, the determinant of the minor that we get by eliminating the I and j row. That's going to be sine theta, r over the square root of a squared minus r squared, and then r cosine theta. And if we just copy these down correctly, we should get the right result. Then it's going to be minus j times the minor that we get eliminating the j row and column. And that's going to be cosine theta, r over the square root of a squared minus r squared, negative r sine theta, 0. And then it's going to be plus k times the determinant of the minor that we get eliminating the k row and column. That's going to be cosine theta, sine theta, negative r sine theta, cosine theta. And I believe this is going to come out identical. We're going to have 0 here. We're going to have r squared cosine theta over a squared minus square root of a squared minus r squared, and that'll be our I component. And that's minus and that agrees with what we have here, so that verifies this calculation. Then this determinant is going to be negative r squared sine theta divided by square root of a squared minus r squared, but it's minus j times that negative. Hang on a minute. Okay, good. I caught an error. And of course, as you know, I just pretended to make that error so I could illustrate the advisability of doing this. I wrote down these vectors carelessly. This vector came from crossing k with I. K cross I is j, so we're going to get a j. And we do get the negative. K cross j is negative I. K cross j gives us negative I. I can't really get my hand into that position under the camera. Giving us the I vector when we do this, and this is going to be negative I, so we should get a negative here. Now I'm going to go off camera for a second and repair that, and then we'll move on. Okay, all better now. You can check for yourself to see just how close, or just how close I came to missing that, and I wasn't pretending at all. It turns out that when we calculate the magnitude, both of these are going to be squared anyhow, so it wouldn't have made a difference in our final result, but there would have been that error in detail, and typically it isn't going to come out quite as nicely if we make those kinds of errors. So just double checking to make sure I've got it right. Now we've got negative j times the negative of this product, and the negative of this product is positive r squared sine theta over the square root of a squared minus r squared, and it's the negative j times that, so that does come out negative. And in this case, this product comes out negative, so we're going to have negative r squared cosine theta over that square root of a squared minus r squared multiplied by I, so I think we're correct now. Okay, now all we have to do is write down the magnitude of this factor and then integrate it with respect to r and theta. So let's see, our magnitude of r sub r cross r sub theta, almost made that into parenthesis, you should understand what I mean here, equals what? Now I haven't written out the entire step. I did mention it. Let's be careful, make sure we understand that these terms are both k terms, so they add, so this is nothing since cosine squared plus sine squared of theta is 1. This is nothing but rk. So our k component is just r, and now we can write it's going to be the square root, and I probably have made a bad decision trying to write it here, but it's going to be the square root of the x component squared, that's just r squared, and then it's going to be the square of this, and that's just going to be r to the 4th sine squared theta over a squared minus r squared plus r to the 4th cosine squared theta over a squared minus r squared. And I really didn't leave myself enough room, and I didn't write as compactly as I should have, but it should be clear that squaring the j component, we're getting r to the 4th sine squared theta over a squared minus r squared, and the I component, very similar, just with the cosine instead of the sine. Now we see that we're going to be able to factor out the r to the 4th over a squared minus r squared, giving us a sine squared plus a cosine squared. And since this step has been kind of blurred out, I'll go ahead and write a little more than I ordinarily would. That's the square root of r squared plus r to the fourth over a squared minus r squared times sine squared theta plus cosine squared theta. This is just 1, so our expression is the square root of r squared plus r to the fourth over a squared minus r squared. And this is the expression that we're going to want to integrate with respect to r and with respect to theta. Since we're going to integrate it, we probably want to simplify it just a little bit. We could begin by either factoring an r squared out of the square root, giving us an r here and reducing our powers of r by 2 here, or by putting everything over the common denominator, a squared minus r squared, and of course that's all within the square root. So I'm going to choose the latter and say we've got the square root then of r squared times a squared minus r squared divided by a squared minus r squared plus r to the fourth divided by a squared minus r squared. If I multiply this out, I find that I've got a squared r squared minus r to the fourth, which is going to be added to r to the fourth all over this common denominator. So the r to the fourth is going to go away, and I'm just going to end up with r squared a squared over a squared minus r squared. And then I'm going to factor the r squared a squared out of the square root, leaving us just r a over the square root of a squared minus r squared. A quick look tells us that we're going to be able to use the u substitution when we integrate this with respect to r. U equal a squared minus r squared. The u is going to be negative 2r dr. We're going to have an r dr up here, so we're just going to end up with a constant divided by u, natural log of u. We'll complete the integral in the next clip.